So in our last video, we talked about the different qualities of a polynomial, even some more characteristics of a polynomial, specifically about the degrees. Now let's go ahead and see if we can use all the information we've learned thus far into giving us a potential graph of a polynomial. This will not be a perfect image. However, it could be a potential that could fit the characteristics of our polynomial. So let's go ahead and look at an example. Let's go ahead and look at an example. First, let's say we have the example f of x equals to negative x cubed minus 2x squared. The first thing that I like to identify when graphing or giving a potential graph of a polynomial is the leading term, of that polynomial. So the leading term, as we defined earlier, is the term that has the largest exponent. So clearly here, that's the value of negative x cubed. So it is a negative x cubed. What I often like to do is right beside this value, I like to go ahead and draw what I expect my end behavior to look like. So as we approach negative infinity, as we approach positive infinity. So notice I have a cubic. So we're thinking it either starts in quadrant 3 and ends in quadrant 1, or starts in quadrant 2 and ends in quadrant 4, but it has a negative leading coefficient. So I know it's going to start up here in quadrant 2, and then it's going to move on to excuse me, quadrant 1. Start off in quadrant 2 and move on to quadrant 1. So start off in quadrant 2 and move on to quadrant 1. That's the first thing I like to do. The next thing I like to do is that I like to identify my zeros. I like to identify the zeros of the polynomial. So in this circumstance, in order for us to identify the zeros, we're going to have to set this equal to 0 and probably do some factoring. So we're going to have negative x cubed minus 2x squared set equal to 0. I'm going to pull out a GCF. I like to pull out negative GCFs because I'd rather work with positive internal, I guess you call it internal factors. So I'm going to pull out a negative x squared, and that's going to leave me with a positive x and then a minus 2 set equal to 0. So negative x squared makes this a positive x cubed. I took out 2, I'm left with 1. And I took out both x squares, so I'm left with that minus 2. So now since I've factored this, I can set both of these equal to 0. So I get negative x squared is equal to 0, and then I get x minus 2 equal to 0. The next thing that I like to do, I don't want to say the next thing, I guess intermediate to me actually finding the zeros, I always like to indicate the multiplicity. So I always like to indicate the multiplicity. So when I indicate the multiplicity here, I recognize my multiplicity here is a value of 2, and then my multiplicity here is a value of 1. So even though I don't see it, I know it to be a value of 1. So this will help me later on with determining the action at my zeros. Solving here, I'm going to divide both sides by negative 1, so I get x squared equals to 0, then taking the square root of both sides, so I get x equals to plus or minus 0, which is just in fact 0. I'm going to add 2 on both sides. I didn't need that equal sign there. And now I get x is equal to a value of 2. So I have two zeros here, one at 0, and the next one is at a value of 2. Then I'm going to indicate my multiplicity, which I abbreviate MP. I realize here it's a value of 2, which is even. And with even multiplicities, I expect my graphs to just touch at those zeros. And here my multiplicity is a value of 1, which is odd. So I expect my graphs to cross at that 0. So now we have an idea about my end behavior. We have an idea of the zeros, and we know their multiplicity. So let's go ahead now and identify a possible graph of this polynomial. So I'm going to do it relatively large. So I'm going to do it relatively large so we can see it. The first thing I'm going to do is I'm going to indicate my zeros. So I have a 0 here at 0, and then I have a 0 at 2. So this is 1, that's negative 1, that's negative 2, and then it continues and so forth. And now I have to first look at my leading term analysis. So I scroll back up to the top, and I said, okay, I expect it to start off in quadrant 2 and then end in quadrant 4. So I know I expect to start off at quadrant 2, and I better end off in this quadrant. If I don't, I probably did something wrong. So the first thing I'm going to see is that at 0, I'm going to touch. So at 0, I am going to touch. So I'm touching at 0. And then I have to come back down here to 2, but at 2 I expect to cross. So I'm going to come back down here at 2, and then I'm going to cross at 2, and then notice I continue all the way down until I get to that value, or get to that rest of the curve that I expected to happen. So notice here, we have two maxes. We have two critical, well, not two critical points, but two curves in our graph. Notice here we have a curve here, a max, and notice here we have a min. So sometimes you might actually be asked to indicate how many curves in the graph exist. And notice there are two curves. There are two, and I hate using the term curves because the whole graph is considered a curve, but we actually have two curves in our graph, or two extreme points, maxes and mins. And remember our degree here, what was our degree? Our degree was a third degree polynomial. We had a third degree polynomial. So a third degree polynomial means we can have three possible real zeros, and that's at most. That's at most. And notice here we had 1, 2. But remember, the multiplicity of this 0 was in fact a 2. So if we add our multiplicities together, notice here we get that value of 3. And then we know that we could have 3 minus 1, which is equal to 2 possible curves. And notice we had one curve, which is a max, and another curve, which is a min. So we are abiding by all the critical values and all the relationships that we discussed in prior sections. So just as a review, the first thing we did was identify the leading term. The next thing we did was identify our zeros and then their multiplicities. And then last, we put it all together on our graph and gave ourselves a potential function.